So let's find all first and second derivatives of this function. Then we're going to find critical points and characterize them. So just because I like the little subscript notation, I'm just going to call that f instead. So I'll take a first derivative with x and then with y, and then and then the second derivatives, and then my mixed partial derivative. That's what we have to find. So the derivative with respect to x gives me 12x plus 6y from that term plus 36. And everything else goes away because we're pretending that y is a constant. Then the derivative with respect to y is going to be 12y plus 6x minus 54. Everything else goes away because we pretend that x is a constant. Now the second derivative with respect to x is just going to be 12. The second derivative with respect to y is going to be 12. And then the mixed partial is going to be 6. So that's all my first and second derivatives. The critical points, those are the points where both of my first derivatives are equal to 0. So critical points are where this thing is equal to 0 and that thing is equal to 0. So I can write 12x plus 6y plus 36 equals 0, and also 12y plus 6x minus 54 is equal to 0. And this gives me a system that has 2 equations and 2 unknowns, so I should be able to solve it. I'm going to divide both equations by 6 because everything is a multiple of 6 here. So 12 divided by 6 gives me 2x plus y, and then 36 divided by 6 is 6. And then I'll have 2y plus x, and 54 divided by 6 is 9. Okay, so same deal. Still have 2 equations with 2 unknowns, but this is simplified a little bit. I'm going to take the first equation and solve for y. So that first equation would give me y equals negative 2x minus 6. And then I'm going to plug that formula for y in for this y in the second equation. So this is just solving with substitution. So my new second equation is going to be 2 times negative 2x minus 6. Plus x minus 9 equals 0. So distributing the 2 gives me negative 4x minus 12 plus x minus 9 equals 0. So collecting my x's gives me negative 3x, and then 12 plus 9 is 21. So that tells me that x must be negative 7. I still need to find a value for y. I found my x value. My y value, I can go back here, change color, and I have this formula that tells me y has to be equal to negative 2 times x, but x is negative 7. Minus 6. So negative 2 times negative 7 is positive 14. Positive 14 minus 6 is 8. So I have x is equal to negative 7 and y is equal to 8. So I've only found one critical point, and I think there's only one critical point for this function that we're talking about. My critical point is at the point -7, 8. When I'm going to characterize my critical point, that means, tell me if it's a maximum or minimum or saddle point. That means I have to calculate that capital M value, which was fxx, evaluated at my critical point, times fyy, evaluated at my critical point, minus the mixed partial derivative evaluated at my critical point. So these second derivatives and the mixed partial derivatives, they're all just constants, so it actually doesn't matter what my x and y value are for my critical point, because I don't see any x's or y's in any of these formulas. So m is just equal to 12 times 12 minus 6 squared. So 12 times 12 is 144, 6 squared is 36. So that must leave me with like 108. Okay, so m is positive, so we say m is greater than 0. The second derivative with respect to x is 12, so that's greater than 0. And whenever we have these conditions, that means we must be looking at a minimum. The second derivatives being positive, that sort of tells me that I'm like concave up, if you will. And the deal with concave up functions is that you have a minimum at the critical points. So whenever it's concave up, it's shaped like that, and this would be the critical point, so that's the minimum. And the m greater than 0 just means it's not a saddle point. If m were less than 0, then we would know we would have a saddle point. And if m were equal to 0, then our test fails. Our test would be inconclusive, and we couldn't really tell what's going on. But anyways, this is how you characterize your critical point. We know that my critical point is the point -7, 8, and that critical point corresponds to a minimum of my function. Again, this is going to be super important for your final exam. Like understanding what we just did here, there's going to be a question just like this on the final, where it's going to ask you about the derivatives, it's going to ask you to find critical points, and it'll ask you to characterize your critical points.
Is it like a level question, or are they all like open-ended?
It'll be open-ended.
I do better with options.
Yeah. Okay. Again, no questions. This all made perfect sense. You're going to remember this next week. Okay. Be ready to do that next week. This is our very last section of the whole types book, 14.4. It's called The Method of Lagrange Multipliers. And I think this is really neat. I'll tell you why maybe at the end of class. But the method of Lagrange multipliers is used when you want to optimize, which means find a maximum or minimum of a function. If you want to optimize a multivariable functions, and this is the kicker now, is while adhering to some constraints. In section 14.3, we learned how to find maximums and minimums, so we knew how to optimize functions. But the method of Lagrange multipliers is going to allow us to introduce some constraint and still find an optimum. So here's the procedure. This is what's called the method of Lagrange multipliers. You're going to say, I want to optimize the function f, and it's a multivariable function, so you could have two independent variables, x and y. And I'm going to optimize this function subject to the constraint where I have some function of g of x equal to 0. So it's really key that one side of our constraint equation has to be equal to 0. Step number 1, we're going to write what's called the Lagrange function. And I'm going to use a capital F to represent the Lagrange function. So my Lagrange function will then be a function of 3 variables, x, y, and lambda. So this shape right here, this is a Greek letter lambda. Lambda. It's a lowercase lambda. And that's what we're using right here. Anyways, capital F is the Lagrange function. X, y, and lambda are my new independent variables. And the Lagrange function is going to be my lowercase f of x function. Sorry, f of xy function. That's the function we're trying to optimize. Minus lambda times my g function of x and y. So the lambda shows up here. And this lambda is what we call a Lagrange multiplier. So whenever we talk about the method of Lagrange multipliers, the Lagrange multiplier part of that is the little lambda that pops up right there. So step number 2 is after I have the Lagrange function, I'm going to calculate the partial derivative of that Lagrange function with respect to x and the partial derivative of that Lagrange function with respect to y. And then number 3 is we're going to solve a system of 3 equations. So the 3 equations are this, and the 3 unknowns are x, y, and lambda. So it's just going to be a matter of algebra, figuring out some substitutions so that I can figure out the values for x and y. Your textbook has the same system of equations written like this. In your textbook, they'll write partial with respect to x is 0, partial with respect to y is 0, and partial with respect to lambda is 0. These mean exactly the same thing because if I took this Lagrange function and I take the partial derivative with respect to lambda, well, my f of x function, that goes away because there's no lambdas there. And I pretend that x and y are constant. And then again, pretending that x and y are constant means this whole g function is a constant. So taking the derivative of lambda just makes it 1. And I end up just setting g of x equal to 0. So that's why I say that these 2 systems of equations, where I just replace the partial with respect to lambda with g, those are the same thing. So, just want to point out what your textbook has in blue, but it's exactly the same as what I've typed out here for my system of equations. And then the last step, you're going to have at least, well, not necessarily, but if it's a well-written problem, you'll have one point x and y that satisfies this system of equations. Sometimes you'll have more than one point that works out here. Sometimes there's more than one maximum or more than one minimum. But you're going to have to just use sort of context clues to figure out whether it's a maximum or a minimum. Like maybe try plugging those values into f of x, right? So maybe try that and see if it seems to be giving you a really large value or a really small value compared to the other values of the function that you maybe know about. And you just have to, again, be a little bit clever in using your context clues to figure out if you're talking about a maximum or minimum. So let's do an example, because maybe it's not super clear, like what do I mean by constraint, or what do I mean by the function we're supposed to optimize. Example number 1 says, find the maximum and or minimum values. So basically optimize the function. And the function we're trying to optimize is this, x squared minus y squared. And we're going to optimize this function subject to a particular constraint, which is going to be that. So before we start on this, I really want to visualize what we're doing. I think it's helpful to try to see what's happening here. So my function is x squared minus y squared. man, this website's been working so well for the past week or so, and then now it's not going to work for me. There we go, okay. X squared minus y squared. So this is the function that I'm trying to find a maximum or minimum of. And you can see that there's a saddle point at the origin. In the y direction, it's decreasing. And in the x direction, it's increasing, so you get this little potato chip shape. And maybe that helps. Anyways, there's really, if you just look at this function by itself, there's no maximum or minimum. Whatever minimum point you think you found, you can always find a point next to it that's a little bit lower if you just go farther in the y direction. And whatever maximum point you think you found, you can always find a point that's even higher than that if we keep going out in the x direction, right? So this shape by itself does not have any maximums or minimums. But if we plot some contour lines for this, so if I make contours like x squared minus y squared equals 1, x squared minus y squared equals -1. Hold on, I think I know a smarter way to do this. What if we try this? -2, -1. Nope, that doesn't work. I thought for sure that would work. Use square brackets. Yeah, there we go. Okay. So this is an easier way to make contour lines. Let me pop a few of these contour lines in here. So we talked about contour lines maybe a week ago. Contour lines are places along this surface that have the same z value. So you lock in place the z value, and the contour lines tells you where along that surface has that particular z value. So if I drew contour lines on this surface and I projected them all onto the xy plane, these would be the contour lines, right? It gets pretty flat near the middle where the saddle point is, and then as you're going in the x direction, it gets rapidly, pretty steep. And then as you go in the y direction, it also gets rapidly pretty steep. It's only really flat around the middle. So this is what the contour lines are telling us. Now, the other part of this question, I'm not only trying to find maximum or minimums of that function that we've been looking at, but I'm also trying to find those subject to this constraint. So let's plug in this constraint into Desmos and see what that looks like. My constraint was x minus 1 squared plus y minus 1 squared is equal to 4. And so my constraint is telling me that my x and y values have to fit somewhere on that purple circle. Okay? So the question is, which x and y values give me the maximum value of my surface, that multivariable function, but I'm only going to consider the x and y values that fall on this circle. So we know that this surface was increasing in the x direction and decreasing in the y direction. And so this contour line that's farthest along in the x direction, that's going to be the largest contour line. And so probably the maximum value along the circle is going to fall like right around here, I think. If I keep making more and more contour lines, maybe I'll add another contour line when z is equal to 7, and z is equal to 8, and z is equal to 9. There we go. And 10. So this last curve on the right, this represents a z value equal to 10. And that would be the greatest z value of any of these contour lines, but it's not touching my circle. So then I look at the next little curve in, and this would represent a z value of 9, but again, it's not quite touching my circle. The next contour line in, this represents a z value of 8, and it does intersect my circle just barely at those 2 points. And so again, my most likely place, just visually, is going to be somewhere around here for my maximum value of my function. restricted to that circle. So the red contour lines represent my multivariable function. This purple circle is representing my constraint equation. Now is it clear what we're looking for? Trying to find a maximum subject to a constraint. Okay. So knowing that that's what we're looking for a point somewhere around here. Let's try to do the math according to our little procedure, and we'll see if it works out. So this is the function I'm trying to optimize. My constraint equation, before I start my whole procedure, like in step 1, I need to make my constraint equation look like some function of x and y equal to 0. And I said it was very important that one side of this constraint equation is 0. The way that it's given to me, this equation, this constraint, does not have a 0 on one side of the equation, but it's actually really easy to fix. We can write x minus 1 squared plus y minus 1 squared minus 4 equals 0. So if I subtract 4 from both sides of that constraint equation, now one side of the equation is 0, and it means that this left side of the equation is what I'm going to call g of x comma y. So the next thing I have to do is I'm going to write my Lagrange function. So I write capital F. This is going to be a function of x, y, and lambda is equal to lowercase f of x and y minus lambda times g of x and y. So f is equal to x squared minus y squared minus lambda times x minus 1 squared plus y minus 1 squared minus 4. So I need to find the partial derivatives. What is the partial derivative with respect to x? I'm going to pretend that y and lambda are constants, and I take the derivative with respect to x. So x squared becomes 2x. And then over here I see x minus 1 squared, so my power rule is going to make that 2 times x minus 1. And then I have to remember the minus lambda. So this is going to be something like that. So I use the derivative power rule to make x minus 1 squared into 2 times x minus 1. And I don't care about all of the other terms because, again, I'm pretending that y is a constant. And lambda stays around because I'm pretending that lambda is a constant. So taking the partial with respect to y is going to be similar but not quite the same. Negative y squared is going to be minus 2y. And then this last bit's going to be the same. It'll be minus lambda times 2 times y minus 1. So stop me if something doesn't make a lot of sense to you. So step 3 in my little procedure says that I need to set this partial with respect to x equals 0, the partial with respect to y equals 0, and I need to keep my original constraint equation, g is equal to 0. And this represents a system of 3 equations with 3 unknowns. Those 3 unknowns are x, y, and lambda, so that means I should be able to solve it. And putting this together, I have 2x minus 2 lambda times x minus 1 equals 0. I have negative 2y minus 2 lambda y minus 1 equals 0. And then my constraint is x minus 1 squared plus y minus 1 squared equals 0. These are my 3 equations. I'm going to just rewrite these to simplify. So if I divide both sides of this first equation by 2, I can get rid of the 2's, and then I'll distribute the lambda. So I'll have x minus lambda x plus lambda equals 0. Then same thing, divide both sides by 2, distribute the lambda, gives me negative y minus lambda y plus lambda equals 0. And then my, oops, I forgot a part of this, or minus 4. There we go. I'm going to rewrite that one more time. I'm going to factor out this x to give me x times 1 minus lambda. And then I'll subtract lambda from both sides, so that's negative lambda. And then if I divided both sides by 1 minus lambda, it gives me this formula for x. And I can do basically the same thing for y. I can factor out the y, and this would give me 1 plus lambda equals negative lambda. The negatives cancel, and then I divide by 1 plus lambda, and that gives me a formula for y as a function of lambda. So I could get my x and y really easily if I could just calculate lambda. That's, I think, going to prove to be the really difficult part of this. But I will, we'll try our best here. So let me replace this x with my formula that I got for x in terms of lambda. So over here, I'm going to have negative lambda divided by 1 minus lambda, minus 1 squared, plus. I'll replace that y with the formula I got for y in terms of lambda. So I'll have lambda over 1 plus lambda minus 1 squared minus 4 equals 0. So this is, again, I'm trying to solve a system of 3 equations with 3 unknowns using substitution. And what I've gotten so far using that substitution method is I have now just an equation where I have one equation, I have one unknown variable, I'm just looking for a lambda. Now it's just a matter of simplifying this one really obnoxious looking equation. So let me, I guess the right thing to do right now would be to expand out these squared factors right here. So whenever I take this and square it, I'm going to have negative lambda squared is just the same thing as positive lambda squared. And then in the denominator, I'd have 1 minus lambda squared. And then I'll do minus, or I guess plus, because negative 1 times negative lambda would be positive. So plus, that happens 2 times lambda over 1 minus lambda. And then negative 1 times negative 1 is positive 1. So those first 3 terms are just expanding out this squared factor. If you take that and multiply it times itself, this is what you get. Then I'll expand out this portion. So I'm going to have lambda squared over 1 plus lambda squared minus, so there's a negative 1 there, minus 2 lambda over 1 plus lambda, and then plus 1, because negative 1 squared. Finally, minus 4 equals 0. So some of these are difficult problems. I'm going to multiply everything by every single term in this whole equation. I'm going to multiply everything by 1 minus lambda squared times 1 plus lambda squared. So the first term is going to then become lambda squared times 1 plus lambda squared, because the 1 minus lambda squared is going to cancel with that denominator. The next term is going to become 2 lambda times 1 minus lambda. The other 1 minus lambda will cancel with the denominator, and then 1 plus lambda squared. The 1 plus 1 minus 4 is really a negative 2 as my constant there. Maybe I'll save that for the end. And I have plus lambda squared times 1 minus lambda squared. And the 1 plus lambda squared will cancel with the denominator of that term. Minus 2 lambda, and then I'll have 1 minus lambda squared times 1 plus lambda, and the other 1 plus lambda cancels with the denominator. And now coming back to that constant, I have minus 2, because 1 plus 1 minus 4 gives me negative 2, negative 2 times 1 minus lambda squared, 1 plus lambda squared. Yikes. All of that equals 0. So I know this looks like it's going to get messier and messier, and it really might. That's why I gave you a whole page for this example. Tried to save room for it. Now we're going to try to expand out all of these, and it's going to be a huge pain. It's just, I guess, the way it is. So lambda squared times 1 is a lambda squared. Oh, sorry. That's also squared. So here we go. 1 plus lambda squared. What is that? Just by itself, that would be 1 plus 2 lambda plus lambda squared. So then if I multiply all of those terms times a lambda squared, this first term is going to be lambda squared plus 2 lambda cubed plus lambda to the 4th. Okay, second term. I saw that 1 plus lambda squared. Now I'm multiplying it times a 1 minus lambda. I'm going to get really tired of saying the word lambda. So 1 minus lambda times 1 plus lambda squared is going to be like multiplying this thing times 1 minus lambda. So 1 times 1 gives me 1. 1 times 2 lambda gives me 2 lambda. Minus 1 times lambda is going to be plus 1 lambda. Then I have 2 lambda times negative lambda gives me minus 2 lambda squared. Plus 1 lambda squared is going to give me minus lambda squared. And then finally there's going to be minus lambda cubed. So then here for this next term, I have 2 lambda plus 2 lambda squared minus 2 lambda cubed. Minus 2 lambda to the 4th. Okay, so I've multiplied every term here by 2 lambda so that I can get that second term. Yikes. I'm going to switch colors. Mix it up. So now for this term, I need to find out what is 1 minus lambda squared. And 1 minus lambda squared would be 1 minus 2 lambda plus lambda squared. So multiplying all of those times lambda squared is going to give me lambda squared minus 2 lambda cubed plus lambda to the 4th. I wonder if there's an easier way to do this, and I've just completely missed the point. There's probably an easier way. Okay, so now I need to find out what would be 1 minus lambda squared all times 1 plus lambda. So that would be this thing up above. Oops, I put the squared in the wrong spot. Times now 1 plus lambda. So for my constants, I have 1 times 1, which is 1. For my lambda terms, I've got 1 times negative 2 lambda plus 1 times lambda is minus lambda. And for my lambda squareds, I've got a lambda squared minus 2 lambda squared, so I'll write minus lambda squared, and then for my lambda cube, I just have plus 1 lambda cube. So now here in green, I have to multiply every one of those terms times 2 lambda, so I have minus 2 lambda. 2 negatives make plus 2 lambda squared. Another 2 negatives make plus 2 lambda cube, and then minus 2 lambda to the 4th. Yikes. Okay. Getting down to the last term. So close. We want to now find 1 minus lambda squared times 1 plus lambda squared. So it's going to be this thing all times that thing. This is really difficult. So I'm going to make a big table. I don't know if I do this a lot in this class, but whenever I'm trying to be very careful and not make any mistakes when I'm multiplying, like two factors with multiple terms, I like to make a big table like this. And 1 times 1 is 1, 1 times 2 lambda is 2 lambda, is lambda squared. 1 times negative 2 lambda is negative 2 lambda. This is going to be negative 4 lambda squared. This one's going to be negative 2 lambda cubed. This is lambda squared, 2 lambda cubed, and lambda to the 4th. So a few of these things are going to cancel. Like 2 lambda cubed and negative 2 lambda cubed, those cancel each other out. 2 lambda and negative 2 lambda, those cancel. And so if I add up everything I have left, adding all this up gives me 1 minus 2 lambda squared plus lambda to the 4th. Okay. So that's going to be 1 minus 2 lambda squared plus lambda to the 4th. And my last term up here is just negative 2 times that. So 1 times negative 2 is negative 2. Negative 2 lambda squared times negative 2 is plus 4 lambda squared, and this last one's going to be negative 2 lambda to the 4th equals 0. Cool. Now we're going to collect like terms. So how many lambda to the 4ths do I have? I have 1, negative 1, 0, negative 2, negative 4. So adding up all my lambda to the 4th terms, I think gives me negative 4 lambda to the 4th. Okay, now let's collect my lambda cube terms. So I've got 2, 0, negative 2, 0, and I have 0 lambda cube terms. Those all cancel. What about lambda squared? I've got 1, 3, 4, 6, 10. I've got 10 lambda squared that I can see. And then what about just plain old lambdas by themselves? I'm running out of colors to use. I've got 2 lambda minus 2 lambda gives me 0. So I have no lambdas by themselves, and my only constant in this equation is a negative 2. Negative 2 equals 0. Cool. That's actually really simple. So we're very close to finding the values of lambda that work. I'm going to divide that equation by a negative 2. So negative 4 divided by negative 2 will give me 2 lambda to the 4th. 10 divided by negative 2 is going to give me negative 5 lambda squared. Negative 2 divided by a negative 2 gives me plus 1. And this equals 0. I'm going to have to erase some of this, so I apologize for deleting that information. But I needed more room to work this monster problem. I didn't think it would be that tough. You know, geometrically, it doesn't seem that tough. But that one was a hard one. I'm going to make a little substitution and say that mu is equal to lambda squared. Mu is also a Greek letter. That's a lowercase Greek mu. And so if I make the substitution mu is equal to lambda squared, then I have 2 mu squared instead of lambda to the 4th minus 5 mu instead of lambda squared plus 1 is equal to 0. That's a quadratic equation, so I can use my quadratic formula. My quadratic formula tells me that this is going to be well, negative b is a negative 5 divided by 2 times a, which is 2 times 2, plus or minus the square root of b squared, so negative 5 squared, minus 4 times a times c over 2 times a. So quadratic formula tells me that this is going to be 5/4 plus or minus the square root of 25 minus 8 is 18 divided by 4. So 18 is the same thing as 3 square root 2. Oh, it is 17? Ah, thank you for catching that. Ha. Very important. 25 minus 8 is 17. Awesome. So I have these really crappy values for mu, and I say they're crappy because they're really ugly. And remember that mu is lambda squared, and what I really wanted to know was lambda. So lambda is going to be the square root of 5/4 plus or minus square root of 17 over 4. So that's not going to be very happy numbers, but we do have a TI 30 calculator available to us, right? So somebody tell me, what is the square root of 17? What's just the square root of 17? .12. Okay. Now, we're going to have two cases. One where we take the plus sign and the other one where we take the minus sign. And so if I do 5 plus 4, then it would be 9.12 over 4. What's 9.12 over 4? 2.28. Sounds good. And then what would be the square root of 2.28? Yeah, the square root of 2.28 is approximately 1.5. What about the square root of 0.22? Okay, great. And both the positives and the negatives of these lambdas are going to be acceptable. And the reason I say that is because this was my equation after I simplified it, 2 lambda to the 4th minus 5 lambda squared. And if you take the negative and then raise it to the 4th power, you take the negative and then you square it, you get the same answer. So actually, there's 4 values that work for lambda. Positive 1.5, negative 1.5, positive 0.46, and negative 0.46. If we plug in all 4 of those values for lambda, it's going to give me 4 points, x comma y, that are maximums or minimums of my function along my constraint. Okay, so using these formulas here for x and y, plug in those values for lambda. So start off, somebody tell me what is x if lambda is positive 1/2. It would be negative 1.5 divided by 1 minus 1.5. Oh, yeah, okay, that makes sense. Cool. 3. What about y? What if I have 1.5 divided by 1 plus 1.5? 0.6. Yeah, okay, cool. What if we use negative 1.5 now? So if I have in the x negative 1.5, positive 1.5, divided by 1 minus negative 1.5, I think that's going to give me 0.6, and then that should give you 3 for the y value. Okay, kind of interesting. Yeah, because the lambda and the negative lambda is just swapped. Okay, so what about my other value, 0.46? Plug in negative 0.46 divided by 1 minus 0.46. Yeah, that sounds right. And what about 0.46 divided by 1.46? .31, okay. So negative 0.85, 0.31, and then we'll have 0.31, negative 0.85. So these 4 points are going to be either maximums or minimums of my function along my constraint. Let's try them out. So 3.6, 3 comma 0.6. Let's see where that goes if I have 3 comma 0.6. Ha! So that is, there's a little bit of round off error because we rounded to like 2 significant figures as we were doing our calculations. But that is approximately where the maximum of my function would be if I were constrained to this purple circle, right? That's pretty close. A little bit of round off error. So it's not quite exactly on the constraint, but it's in the right direction. My other points were 0.6 comma 3, and that falls over here. And that would be a minimum. So let me extend this contour line out in this direction a little bit. Oops. So remember, in the y direction, this curve is getting lower and lower and lower. You're decreasing as we go out in the y direction. So this represents a minimum of this multivariable function as it is constrained along this circle. Okay, my other points were 0.31 and 0.85. Or was it negative 0.31? Or maybe it was negative 0.85. Yeah, there we go. It was 0.31 and negative 0.85. And so that corresponds to another minimum value of my function as it is constrained along this circle. Because again, as we go out in the y direction over here, those contour lines represent decreasing z values as you go out in the negative y direction. So that's the minimum value along the circle. And then there's another point which corresponds to negative 0.85 comma 0.31. And this green dot represents another relative maximum of the function along the circle, because this is the maximum you can attain on the circle in this little neighborhood. I think the overall, the maximum value is going to be over here, because that's pretty close. That's between the contour lines for z is equal to 8 and z is equal to 9. So this value represents somewhere between 8 and 9. And this is going to be the absolute minimum of my function along the constraint, because it's somewhere between 8 and 9, or sorry, I should say negative 8 and negative 9. These are not quite so bad. So this is a relative maximum, but it's only somewhere between 0 and 1. So it's a relative maximum to the points around it, but it's not actually as large as this maximum. And this is also a minimum, but it's still somewhere between 0 and 1. because these contour lines that are closest to the inside, those represent a z-value of 1 and -1. I should say it's between 0 and -1 for this minimum. Anyways, so you can sort of tell, you can sort of tell the shape of a 3D graph by looking at its contour lines, right? You should be able to maybe make the mental connection between this surface and these contour lines that correspond to the surface. And if we just pick a certain value for z, we can generate a contour line like this. And it turns out that the maximum or the minimum, they're always going to occur at a place where the contour line just barely intersects the curve given by the constraint equation. So that's just like a barely an intersection. That would be like the precise point of my maximum. Like I said, there's another maximum that happens over here at this green dot. So let me adjust this contour line so that this contour line barely intersects my constraint circle. And then you intersect right around that green dot. So we did a pretty good job finding the other relative maximum there. And then if I make this contour line a negative value, I can find my minimums, or my minimum contour line intersects my constraint equation. And then again, my other solution is where this minimum contour line intersects my constraint equation. Okay. Man, I'm sorry that example took so long. I expected to do a lot more examples today. We still have 6 minutes left. Let's try to do one more.
What?
So find the minimum or maximum of this function subject to this constraint. I don't like that one. Let's go to number 2. Well, number 2 is covered up in work. I'm going to erase my work so that I can do number 2 with you guys. Find the minimum or maximum of this function subject to the constraint, blah, blah, blah. Okay. So this time my constraint is actually the formula for a line. I can rearrange that so that y is equal to -x plus 2. And it's a line with slope -1 and y-intercept +2. And this multivariable function is a paraboloid. So it's going to look like a parabola in the x direction and a parabola in the y direction. So I expect that there is a global minimum of that multivariable function at the origin, at x equals 0, y is equal to 0. But the origin isn't part of this, because when x is 0 and y is equal to 0, that doesn't fit my constraint. So the global minimum of this multivariable function does not obey my constraint. What would be the minimum value of my function that actually does agree or does adhere to my constraint? That's the question. So using my method of Lagrange multipliers, we say we have a Lagrange function. It's going to be a function of x, y, and lambda. And that's going to be my lowercase f function minus lambda times my g function. Now, whenever I write my g function, I have to write it such that the other side of the equation is 0. So whenever I have x plus y equals 2, I have to rearrange it as x plus y minus 2 equals 0, because it's super important to have one side of your equation be a 0. Then that makes the other side of your equation g. So that means my g is x plus y minus 2. Okay. Now, the partial with respect to x is going to be 2x minus lambda. The partial with respect to y is going to be 2y minus lambda. And g, my original constraint, I also have to abide by my original constraint. And so this is my system of 3 equations with 3 unknowns, x, y, and lambda. Whenever I solve the system, I have to set each of these equal to 0. Well, I have to set these two equal to 0. Sorry. Now in this black box, this is my system of 3 equations with 3 unknowns. My first equation tells me that lambda is equal to 2 times x, or I could write it x is equal to 1/2 lambda. My second equation tells me that y is equal to 1/2 lambda. And then my third equation tells me that x plus y is equal to 2. So let me just substitute in 1/2 lambda plus 1/2 lambda is equal to 2. Well, half lambda plus half lambda is just lambda, so that tells me lambda is 2. This tells me that x has to be half of lambda, so half of 2 is just 1, and then y is also 1, because it's the same thing. So this tells me that my point that's either a maximum or a minimum along my constraint is 1, 1. We see that it abides by the constraint because x plus y has to be equal to 2. 1 plus 1 is 2. And so let's visualize really quick what it is we've done. My multivariable function was x squared plus y squared. So it was this paraboloid that has a minimum at the origin. But the contour lines of that paraboloid would look like concentric circles around the origin. Right? So every contour line represents a constant value of z. And so as you're increasing in every direction, your contour lines look like circles. My constraint equation was x plus y equals 2, which I told you was the formula for a line. And you can see that's the formula for a line. And the point where the contour line intersects or just barely touches my constraint equation, that's going to be the point 1, 1, which is what we found. So I probably should have started off with that example. That example was a lot faster and easier to see how we found that minimum value of my multivariable function with respect to a constraint, because that time my multivariable function was that bowl-shaped paraboloid, and my constraint was just the equation for a line. So there's some other examples that you might want to take a look at and try on your own when you have free time. But look at that. It only took us 5 minutes for that example. Yeah, so some of these are harder than others. That first example was really, really tough. The second example, a whole bunch easier.
So how did we, okay, because we made the F, we made our equations, what is it called again? The unknowns, the 3 equations and 3 unknowns, they were equal to 1, so that's what made our point?
Yeah, so this first, when I took the partial with respect to x, I got 2x minus lambda. We're going to set the partial with respect to x equal to 0. And if I add lambda to both sides, I get lambda equals 2x. And if I divide both sides by 2, I get x equals 1/2 lambda. You can do the same rearranging to find that y is equal to 1/2 lambda. But if x is 1/2 lambda and y is 1/2 lambda, then I can make the substitution 1/2 lambda plus 1/2 lambda equals 2. Half lambda plus half lambda is just lambda. So this tells me that lambda must be equal to 2. If lambda is equal to 2, and x is 1/2 times 2, then x is 1. And if y is equal to 1/2 times 2, then y is 1. Yeah.
Yeah, much easier.
Much, much easier. Okay, so the reason I like Lagrange Multipliers so much, I think this is super neat. I wish we could spend more time on it. But whenever I was doing my master's degree, I was working on a little problem. And the problem was essentially this. Imagine you're working in like a chemical plant where you have some mixer that mixes up 2 different streams. Maybe this one's like oil and water or something like this. And so you mix them up. It goes into a big drum, and then the drum separates the oil and the water again, and then you can like extract them. So maybe if you have some sort of contaminant in the oil that's more soluble in water, you could remove the contaminant by mixing it with water and then removing the water. Well, a lot of times what these chemical plants do is they will measure the flow rate in like pounds per second on each of the streams. You can just put a little flow meter on each pipe and measure how many pounds per second are moving out. Well, you know that no mass you can leave if you need to.
Okay.
Yeah, you can leave if you need to if you're on your way somewhere. You know that no mass can accumulate inside the drum, And you know that mass has to be conserved. We can't create mass, we can't delete mass. And so that means these flows in, I'll call them A and B, have to be equal to the amount of mass that's flowing out. I'll call it C and D. So if you're measuring A, B, C, and D, it has to be true that A plus B equals C plus D. There's no other way around it. You can't delete mass from the universe. You can't add mass to the universe. Basic physics stuff. So this represents a constraint equation. And in real life, you don't actually know the true values of the mass flow rates through the pipes. These flow meters always have some kind of error associated with the flows that are flowing through them. So if the true value is 10, maybe it tells you it's 11, right? Like you don't ever have a perfectly calibrated instrument. There's no way to have perfect precision when you're making a measurement. So in real life, if you were to just take what the flow meters tell you and add them together like this, it won't ever match this constraint equation. It will always tell you something that's wrong, that's non-physical. And so what I did in my master's project is I set up a multivariable function that, we'll just call it Q, that did this. It took all of the measurements, A, B, C, and D, and it made up values A bar, B bar, C bar, and D bar. And I found the difference between my made-up values that I just invented and the measured values. Squared those, add them together, it gives you some value in this function. I said, what values A bar, B bar, C bar, and D bar can you find that minimize this multivariable function with respect to this constraint equation? But then I didn't just use one constraint equation. I was doing this for an entire oil refinery worth of constraint equations. So there was something like, 6,000 constraint equations and like 10,000 flow meters. And so we were working on this huge system of equations that came from this same method of Lagrange multipliers. But the purpose was whenever you do this, you actually get values for your measured flow rates that make sense, like in the physical world where you can't delete mass or introduce new mass. It actually makes sense. So sorry for keeping you for an extra 5 minutes. But Lagrange multipliers is really interesting, and there's a lot of places in industry and business where you want to optimize, maximize, minimize things subject to a constraint. And so it's very applicable, as well as difficult.
I'm kidding.
All right. So next time we're going to review for your exam. Y'all have a great day.
Just come with questions and everything.
Yeah, I'll probably type up a review before Thursday, probably. But you're right too. If you have questions about a specific concept and you want to see me work a particular problem, definitely come Thursday with those questions, and I will be more than happy to custom tailor the review to you guys.
Sounds good. See you Thursday.
Okay. Have a good one.